All right, so this is a continuation of the previous stream. So there was a problem, question 2, that required or could be solved with a heap data structure, and I used the Python module heapq, but let's try to build one from scratch. So let's see. So a heap, it's a binary, a complete binary tree that I think I know I said something along this line. So we have a binary tree, and let's say that here so complete means that all the nodes are part of the tree except for the last level. The last level can be incomplete, and we're gonna represent it as an array. So here, and we're gonna be doing a min heap. It's the same if it's a max heap. You just have to turn around the comparisons. So maybe here we have a 1. Here we have 3 and 5 and 8. And here we have 2 and 7. So notice the condition that the heap must satisfy is that, and well, let me first explain the array thing. So here we have 6 elements. So yeah, let's make this a 6-element array. Like this, sorry. So this is going to be the root. Let's make it 0 base because that's how it works in Python. So here we have a 1. Then the children of node 0 are going to be 2i of node I, 2i plus 1, and 2i plus 2. So when we are at 0, the children are 1 and 2. So these are 3 and 2 because they are these nodes. Then the children of this node, which is the node at index 1, are going to be 3 and 4. So here we have the 8 and the 5, and finally this is going to be 7 because this is the left child of node at index 2. So the left child is 2 times 2, 4 plus 1, so it's 5. Okay, so that's how. So we're gonna have some functions. So left of I is going to be this, and right of I is going to be this. And then we also want to go to the parent of I, and that's gonna be given by I minus 1 divided by 2, integer division, because notice that if you consider this 2, if you subtract 1, then divide by 2, you're gonna get I, which is the parent. And same here, if we subtract 1, then we divide by 2, we're gonna get I. So for both elements, we get the parent. So that's exactly what we want. And notice that the condition, so if this is we get the root of the heap. So we want to know if if the condition of the root holds, and for that to be true, hey Pat, how's it going? So we want the let's write it this way. Well, no, let me write it in the way that we're going to be implementing it. So the subtree with root at I is a heap if let's say that this array is called H. So H of I is less than or equal to H of the left child of I. No, you don't. You don't have any guarantee of where the max. I mean, I'll have to think about it, but there is no guarantee. There is no way to find the maximum element quickly, if that's what you're going for. Okay, so this must be true. Then the same for the right. And then, so this and this, and then this must, let's say that this also has this. So left of I, also a heap. The right is also a heap. Okay, so if this condition holds, notice that the root is guaranteed to have the minimum element. So that means that you can access, so remember that the root is just the first element in the array. So H0 is going to always be the minimum. Okay, and now let's say that we want to remove. It's useful when you are making modifications to the structure. So for example, when you remove the minimum, you are going to change the last element. You're going to put it right at the top, at the first element. You're going to pop this so that now you have one element less. And now you're at the situation where you have some element here at the root, and you don't know. So the heap condition might not be satisfied now. So you do know that these are heaps, right? Because you haven't changed those. So these were heaps, so they are still heaps, but it's not necessarily true that A, so let's say that here you have a B and you have a C. So you don't know if A satisfy the condition, this condition that is less than or equal to the left child and less than or equal to the right child. So there's a procedure that we'll call it heapify, that it's going to receive a heap in this situation where you have both subtrees are heaps, but the element at the root might not be, and it's going to determine. So if A is less than or equal to the other two, so it is not guaranteed, but it could be true. So if it's true, then you stop. You have a heap. But let's say that C is less than A and B. Then you're gonna swap this element. So here you're gonna have now C, and here you're gonna have now A. So we chose C because it was less than B. So now the condition holds for these three elements, and we haven't modified this left subtree, so that's still a heap. But now we're at the same situation as before with the right heap. So we do this recursively, and that way we go down the one path of the tree until we reestablish the heap operation. So let's see how this is going to look in the so maybe we can just reuse the code. It's not, so I'm gonna call this build heap, and let's call this pop, and let's call this push. Okay, so first we're gonna write, so let's write the helper functions, and also the parent. Okay, so now we have this, and then let's write heapify, which is the process that I described. So we're gonna need the array, let's call it H, and the current node, the current root of this subtree. And so we wanted to see, so if it has no children, so we wanted to first check if the left subtree is the smallest. So if the left of I is within the array, it means that it has, because it could not have, it could be that it doesn't have any left child. So if it has a left child and the value of the left child is less than the value of the current, then we say that the smallest is the left of I, and otherwise the smallest so far is I. Right? We compared I with the left child. Now we want to compare with the right child. So if it is, again, if it has a right child and the value of the right child is less than the value of the smallest so far, then it means that the smallest is actually the right. And now we want to swap the current root with the smallest, but only if it's different than the current. So if it's not I, then we do a swap, which in Python you do like this. Okay. And now we recurse heapify to the smallest. So now we have the same situation at the smallest child. Okay, so this is going to be our bread and butter here. So now building a heap, and this is, notice that this is order of log of n, because we only recurse on one of the children. So we go down over one path. So the order, so the number of steps in the worst case is the height of the heap, which is the logarithm of the number of nodes. Okay, so now the heap. we call this build heap. We just want to go over all the nodes from the bottom, from the last to the first, and do heapify, and do a heapify, right? Because here, so remember that to do a heapify, we wanted the two subtrees, the left and the right subtrees, to be heaps. So if we start, in the case of this, if we start from here, from the bottom, then the left child, so before we remove this, the left child, it's only one element, so it's trivially a heap. So we can apply heapify to reestablish to reestablish the heap condition to this subtree. Then we move to the previous node, and again the children, the left subtree and the right subtree are already heaps, and it's trivial because there's only, if you only have one node, then the heap condition is satisfied. And now we apply heapify to this so that we establish the heap condition to the whole subtree, and then we move to the one level up, and so on. And that's going to build our heap condition to the whole tree. So we want to go over, so we want the parent of the last node, which is length of h minus 1, up to the beginning, up to the root, and we just heapify. And that's it. That's how you build a heap. Notice that you would think that this is n log n, because heapify is log n order, and we're going over all the nodes, or half the nodes. And so you would say that it's n log n, but it turns out that I'm not going to dive into the theoretical analysis, but turns out this is linear, because if you think about it, the intuition is that when you go up the tree and you call heapify, you're going down up to the leaves, but there are the number of nodes in the successive, when you go up levels, decreases exponentially. So even though the paths are longer, the number of times you go down is decreasing exponentially, and that's why it compensates and it ends up being linear. So now let's see if we want to pop. If we want to pop an element, what we said, remember what we said here, that we will get we would get the last element, and we are going to step over the first element because we want to pop so the result, we want to return the minimum, which is at 0, but now we want to remove it. So we're going to step over the last element, and we're going to remove the last element of the array, and then we want to heapify because we know that the root might make the condition. So we call heapify to reestablish, right? And now we just return res. Okay, so that's our pop, and we're only missing the push operation. So the push is a little different. So we are going to append the value to the end, but it could be breaking the heap condition. So we want to, so this element is at this position, at the last position. So we want to go up, comparing it with its parent while it has a parent. So while the parent of I is greater than or equal to 0, and the age of the parent. So if, well, let's say this is h of I is less than its parent, then it's breaking the condition. So we swap them. So we swap them, and we keep going while this happens. So we keep going up, and while this happens until the condition is met. And so this is all. 2 and 4. And we're good. So this is it. It's not a big deal. Once you know the ideas behind it. So here's the code. So I review it. So I know this from school. I read it from the CLRS book, but I just looked. I just review it to remember a nice way to implement it, and this is what I end up with. He knows it. Yeah, so I mean, you don't need to. I mean, it's usually not needed to know this to use it. So AKSR, how's it going? Welcome. You missed the stream, I think, or maybe you were lurking. So it's just, I mean, it's good to learn algorithms. So you can, so some algorithms maybe you won't use in the directly in an interview, but the more algorithms you learn, the more ideas, and you learn a way to think about algorithms. So I think it's worth it to know. Oh, they made you BetSim. How's it going? So they made you implement this? That's nasty. Yeah, if I had to implement this without reviewing from, I guess I wouldn't be able, but the code would be a little not so clean. Anyway, so I just wanted to explain this because I think it's harder than you think initially. Notice that there's a sort algorithm, heap sort, that is based on this. That you just use this and you just heapify. You just build a heap, and then you just remove the elements in order, and that's an actually optimal sorting algorithm, which it's also useful to know some sorting algorithms. Sometimes they are useful. Anyway, so yeah, that's all I have for now. Thanks for watching. I hope you learned something, and see you probably tomorrow if I do a stream of tonight's contest. So bye bye.